Hello everyone, this is Professor Ma and this is the short introduction to the sections on the unit tangents and the normal or unit normal vectors to the curve. We had a theorem saying that if a vector value equation parametric curve has constant length, then the tangent data with the curve is zero, or in other words, that the tangent vectors and that with the vector value functions are perpendicular. So tangent perpendicular to the curve, if you like. So we're going to use that. And so given a vector value function, we can find out its derivative, the tangent vectors. Now we're going to unitize it. We're going to, for example, if I have a curve and I'm traveling along this curve, and at different junctures, I have different tangent vectors with a different length because I'm traveling in different speed. And let me stick something in the middle there. Here, tangent over there. So okay. So I got these different tangents of different lengths. So what I do is I unitize them, and of course in the standard notations, that is, these vectors will be, so for the blue one it will be this one on the unit vectors, and for the red one will be pointing down that way, for the green one will be pointing down that way. So the unitized tangent, these functions, basically I'm watching these points traveling on this curve, on the circle. And the consequence of that is if I were to take the derivatives, they will be perpendicular to the unit tangent. Okay, so here is a calculations of the unit tangent first, the t. And so it's very straightforward. I calculate the tangent. I calculate the length of the tangent divided by the length, tangent divided by the length. That's unit tangent. But now it's slightly messy, complicated. Okay, and just know that because of the length functions in here. And I can plug in the, say at t equal to 1 to obtain the tangent vector and the unitized tangent vector. The principal unit normal now is the unit tangent derivatives. That is, because the unit tangent has constant length, so it's length 1, so n, which is the derivatives of the unit tangent, is perpendicular to the unit tangent, or it's perpendicular to the tangent. Okay. So n is called the principal. If I unitize the n's, one more time, if I don't have this part not unitized, I will produce a perpendicular vectors to the unit tangent or to the tangent, same directions. And now if I unitize it, make a length 1, and then it comes down, if I draw the pictures of a curve with 2 variables, and then it comes down with 2 directions. Okay, and which one of these is the unit normal? And when, of course, then that's the one that curve is turning as we travel along the curve. So in this case, it's the end. Okay, so these are the basic geometries behind the unit tangent and its derivative unitized again, which is the unit normal. Okay, and in 2 dimension, instead of calculating these, find the unit size tangent, then find the take the derivative of these and unitize again, and we can recognize this very easily visually. Okay, because this really for a vector, there's only 2 directions that are perpendicular to it, and the way you get these 2 directions, you just switch the coordinates around, and then one of them is set to be negative. So when you start with the AB, you get 0. So you get 2 of them. Okay. And so, in other words, so if this problem is say in 2 dimension, curve in 2 space in the plane, then we can find out the unit normal very easily. Okay, you calculate the tangent, and for instance, here's the point -1, 1 at t equal to -1, and the tangent vector I can calculate, and when I'm plugging -1, and you will get the tangent vector after you normalize it, you get a unit tangent. Okay, now what's the unit normal? Well, instead of taking the unit tangent, taking these unitized, I have to take c prime of t divided by length of c prime of t, and I have to take the derivative again. These things is called, again, this is called t. And it's kind of complicated, but on the pictures, I know exactly what that unit tangent, unit normal has to be. It has to be, first of all, pointing where the curve is turning, and the length is 1. To get the coordinate, or I have to just switch the coordinate and of the tangent and divide by the length. That will be the unit normal to bypass all those calculations. Taking second derivative and stuff like that. Okay. And in 3-dimensional, of course, we have many, when we calculate the unit tangent, and we take the derivative of unit tangent, we get a normal curve, which is perpendicular to the unit tangent. And but in 3 space, there are infinite many normal curves. I have this tangent in space, and the plane that's perpendicular to the tangents, and any vectors on that plane is perpendicular to t, could be normal. So if I go through the second derivative of the unit tangent, which unit normal do I get? Which one in this plane is the one that's the unit normal? You could calculate it, and that turned out to be very interesting. And that's the normal is always exists in so-called the osculating plane. In other words, here's a picture. Here's a point P and here's a tangent, and I want to find out whether unit normal that's perpendicular to the T it's going to be. What I do is I take a couple of points very close to point P, then there's a plane cut through the 3 points. And in that plane, there is a normal curve, normal vector that's perpendicular to the tangent. And then I move the point Q and P closer and closer, so the plane is more and more fit the point P on the curve. That plane is called osculating or the kissing plane. It's a limit of all the planes as you take the point P and Q and closer and closer toward the point P. And the limit of the plane is called osculating. And the unit normal exists in that osculating plane, perpendicular to the tangent. Okay, and that's it. That's the geometry behind the unit normal and unit tangent. Okay, bye-bye. Later.